next, L6. Now all these are moments of inertia, so I'm just going to write down cylinder. Since this whole chapter, we're calculating one moment of inertia after another. Now the cylinder, if we go with the cylinder about the axis through the center, let's go ahead and put some parameters. The length is L, and radius is R, and the mass is M. We already know this answer because we already did the disk. And when we did the disk, we found it was 1/2 the mass of the disk times R squared. Well, we just add up all those disks, you stack them on top of each other. They're going to be simply a sum of the masses of the disk, which should be the total mass. So the answer, we have the answer here. And we'll call this x-axis. So about the x-axis is going to be 1/2 mr squared. And the x-axis is through the center of the cylinder. The center from the top, down. But what about doing it about another axis? So this is going to be 1 about x-axis, and just to emphasize what that is, and that's through the long center. Straight down like that. That's what this is. But what about through the short center? In other words, you have it this way. See, the axis now is going like this, and you're going to go around like that. That looks very, very scary. Now, we wouldn't want to do this from scratch, doing integrals, but if we use the parallel axis theorem, we can get this by a simpler integral. Let me show you what to do here. What you would want to do is consider a disk like this, and you say, well, that's still hard. That disk's still hard, but it's not hard if the disk is at the center. If we looked at the disk right here, because that's just flipping the coin. That's just spinning the coin. We already did this problem, the old spin the coin trick. So when you do, let's say, I coin spin, we got that to be 1/4 the mass of the coin times the radius of the coin. This was in our previous section. We just did this in section L5. So that means for this little piece here, you would have 1/4. You would have R squared times dm, where there's here a delta m, which, infinitesimal chunk of mass. But we can't integrate that one. That's just the one case in the middle. But how about the general case? Well, see, this one here is kicked over. Let's take this and rotate this to the right, because then it'd be consistent. This would be my x-axis. If I rotate this to the right, I have my x-axis, and then this will be my y-axis going up like that. So here, the distance that this little piece is from the center is x, because the center would be x equals 0. So this contribution to the moment of inertia, I'll call it di, is going to be equal to the 1/4 mr squared, which we'll set up as a 1/4 dm r squared, plus kicking the dm out a distance x. So I'm using here the parallel axis theorem that says for the moment of inertia, I want the moment of inertia about the center of mass plus md squared when you move the axis. So the moment of inertia about the center of mass is spinning the coin. That's your 1/4 mass of the coin, r squared. Well, the mass of the coin is dm. R squared, r is the same. This is the same. You know, this r here is the same all the way through. So the 1/4 dm r squared is your center of mass part. And then your mass is your dm, and you're going to kick it a distance x down the road. So then I need to integrate all these up. Now I like to use here, since it's a solid, I use rho for the density. And the density is big M over the volume of the cylinder, pi r squared times L. So that means dm is going to be equal to this density times the differential volume. Well, what's the differential volume? Well, the differential volume would be pi r squared to get you your area of the plate, and then a little delta x. So here, going from there to there, that's your delta x. It's your x-axis. So that's the setup. So this has to be put in both of those places, but we can just go ahead and factor and say di is going to be equal to big R squared over 4 plus x squared, and the dm is in common to both of those. So now we put, for the dm in here, we're going to have r squared, big R squared over 4 plus x squared. Then we have the density, and then the differential volume, the pi r squared dx. Now we're going to integrate this. So the total moment of inertia is going to be the integration. And here what I'm going to do is, when I integrate this, I notice that the symmetry is that the moment of inertia for the right side will be the same as the left side. So I'm just going to double and go here from x equal to 0 to x equal to L over 2. And then we're going to have r squared over 4 plus x squared. And then we're going to have this stuff, the rho pi r squared dx. All right, doesn't look so bad now. So let's pull out all these constants. 2 is out there already, rho pi, and the r squared is a constant. That can come out. And we want to go from 0 to L over 2, integrate r squared over 4 plus x squared dx. So if we do this integral, we're going to have r squared over 4, and an x is going to pop out like this, and then we're going to have x cubed over 3. So that's going to be this integral. We're going to go from 0 to L over 2. You can take the derivative to go backwards. The derivative of this first part would just be what's in front, r squared over 4, because it's just an x there. And then the derivative here of 3 would come down, kill that 3, and you would have x squared. So it's always good to check like that, double check. So that's going to give us I is 2 rho pi times r squared. Here I'm going to have r squared over 4 times L over 2 plus 1/3 times L over 2, that quantity's cubed, which will be L cubed over 2 cubed, which is 8. Now at this point, I like to put in for the row. Here is the row up here. So I like to put that in for the row. That's going to be big M over pi big R squared L. And then I have pi, I have this part, then I have R squared, like that. And then here, what I would like to do is I notice that there's a 2 that's going to cancel. I'm just going to hit and leave it for now. I'll get it in a second. L over 2 plus 1/3 L cubed over 8. All right, so let's see what's going to cancel here. Well, we're going to have this pi cancel that pi. This R squared will cancel that R squared. And the 2, this 2 here will cancel this 2. And over here, it's going to bring this to be a 4. This is going to become a 4. So I is going to equal, I'm going to have my mass surviving. And I'll leave the L in here for now, so we don't do too many steps at one time. And then here I'll have R squared over 4 times L, because the 2's went out, plus, and then here this became a 4. So this is 1/3 times L cubed over 4. Now I'll bring in the L, and I can bring out the 4. So if I bring out, you know, I think I don't want to bring out the 4. I like this 1 over 12 because that's like the pencil, the rod going around the center of its mass. So let's go ahead and get this to be 1/4 M R squared, so the L's cancel, plus 1/12 M L squared. I like this formula because I can see the extreme cases. Let's write this down again up here. Just simply copy 1/4 M R squared plus 1/12 M L squared. Now suppose the R is very, very small. If the R is very, very small, then I'm going to have like a pencil, a rod. I'm going to have the rod or the pencil, and I know that for the rod or the pencil, the answer is, you know, where this is the length. Now suppose the L is very, very small, so it's very, very thin. Well, if that's the case, if L goes to like 0, then I get the spinning coin, which is the 1/4 MR squared, the coin spin. So I get the coin spin if the L gets very close to 0. And if the R gets very close to 0, I get the pencil. I get this. So I'm thinking this is the pencil or the rod, and this is the spinning coin. So I can check the answer easily in this form. And I also see that the dimensions come out nice because I have the mass times a distance squared. So very, very nice problem. Very difficult to do from scratch if you had to do integrals, but not so bad when you use these theorems. Well, before we leave this section, let's get even more crazy and go about an edge. In other words, here's your cylinder. And let's go ahead and go like that. Whip it around like that. That is crazy. I would like to do this two ways. I would like to do it method one by doing an integration. All right, so here, method one, integration. It's always good to be able to do things more than one way. So here, I basically redo this problem without putting the 2 in front and just simply go from 0 to L. So in other words, I have the spinning coin at the origin, and when I use the parallel axis theorem, here's my term, here's my piece right here, and this piece here became this part down here, and instead of going from 0 to L over 2 with the 2 in front, I'm going to go from 0 to L. So that means, let's take this equation here and have di is r squared over 4 plus x squared rho pi r squared, dx. And now we're going to integrate from 0 to L r squared over 4 plus x squared rho pi r squared dx. So we don't have to redo this again. Everything is the same for this setup and this equation here, which we have copied up here. And this equation here, actually we could have started with this one. We don't need the 2, we go from 0 to L. And this is the same as that one there. Well, this integral is not that hard to do. We already did that. So let's go ahead and bring the rho pi r squared out. And then when we have this integral from 0 to L, we got big R squared over 4 plus x squared dx. So this integral, very similar, we did it before, r squared over 4 times x plus x cubed over 3. Actually, it's easier because we're going from 0 to L instead of L over 2. So this is going to be r squared L over 4 plus L cubed over 3. And then here, the rho is the total mass over the total volume, which is pi r squared L, and there's r squared. The same thing that we did already down in here when we had the mass over the volume, m over pi r squared L, m over pi r squared L. And then here we're going to have the pi. This pi comes there, and this r squared comes there. So the rho is the total mass over the total volume. And then we see we have some cancellations here. Pi is going to cancel, and the r is going to cancel. We're just going to have an m over L. So that means we're going to have 1/4 m r squared plus 1/3, and L is going to cancel, m L squared. And guess what? If we let the r become 0, we have a little pencil or rod going around, and that would leave us with, and that's 1/3 ml squared. We already did the pencil along the edge. That's what that would be. If the L becomes very, very small, we have the spinning coin. which is the 1/4 mr squared for the spinning coin. So the formulas check out very nicely. Now let's do method 2 to do this same problem, and let's use the parallel axis theorem. And to use the parallel axis theorem, this is about the center of mass, and about the edge will be adding m times the distance d from the center of mass. Now the center of mass case we already did. That's up here. Let's go ahead and put cm to just remind ourselves that's the center of mass case. And then let's remind ourselves here, this is the edge. We'll have 1/4 mr squared plus 1/12 ml squared plus m times this d, which is L/2. So this is going to affect the second part, not the first part. So we're taking 1/12 plus 1/4. 1/12 plus 1/4, and then what's in common to both of these is ml squared. Common denominator here is 12, is 1, and 1/4 is 3/12. 3/12 is 1/4. And this is going to be 4/12, and that's going to be 1/3 ml squared, which is what we got there. This agrees. We get the same answer. It's very, very nice. And here I give a summary of the 3 cases in the book where we did one about the central axis that goes through the center of the cylinder, and that's just 1/2 mr squared. And then we did the 2 cases about the center of mass where it's lengthwise, it's turned, because the first one we did was this one here, like that. And the picture summarizes all 3 for us. They have all 3, say, first one, second one, and the third one.